So the last bit I want to look at specifically is about inequalities, but I'm doing it in two pieces. The first one is this idea of using graphs to solve inequalities. So you have to look at areas and things like that. We've seen it, I suppose, for something like this. Not that I'm recommending you would use a graph to solve this, but you could. And that idea being, all right, let's draw the curve. So x squared divided by x plus 2. Well, x plus 2, there's my blue line. Parabola x squared, I'm dividing. So therefore, I can break this up into regions. There's an asymptote at -2. And, okay, I know the areas that it's going to be in. We have an oblique asymptote. If I do a polynomial division at x minus 2, so I'll put that in. And oh, that was a bad choice of colour. It's the same as the blue line. But anyway, there we go, get rid of the construction. There's our curve, the blue one. So what we're basically saying is, when is that curve less than or equal to the horizontal line 1? So we've still got to find those points of intersection. Fortunately, because I've got a rather accurate graph there, I can see straight away that it's -1 and 2. That's, I guess, the disadvantage of using this method. If you don't have an accurate graph, you're going to have to work out the points of intersection anyway. So solving them simultaneously, sure enough, there we go, we get 2 and -1. So we're between 2 and -1, but of course don't forget about this piece of the blue curve over here, which is x is less than -2. So of course that's probably one of the first sort of questions where we solved inequalities using a graph. As I say, probably not the preferred method for a question like that. Okay, more fun than ones like this. So we're looking at the sideways parabola. Y equals the square root of x. They've labelled a few points for us. And they want us to show that that graph is always increasing, even though we can look at it and go, oh look, it's going up. Well, that's not good enough. We've got to actually prove it mathematically. And of course we use our derivative. So we know it's going to be increasing when the derivative is greater than 0. If I differentiate y equals the square root of x, 1 on 2 root x, well that's always positive, because it is the positive square root we're talking about. So as long as x is greater than 0, then the derivative is greater than 0, so thus it's increasing. I mean, you don't really need to do this next bit, but I suppose I say, oh, it has to start somewhere. At x equals 0, it is 0. And when x is greater than 0, y is always greater than 0. And so thus we know it is increasing, but I suppose you don't really need to talk about the starting point. Once I've determined, once it goes after the starting point, the derivative is positive, well, it's going to be increasing. Okay. Hence show, here's the fun bit. Hence show the square root of 1 plus the square root of 2, and so on, is greater than the integral. So this is one of these area of the rectangles and the area of the curve. So let's draw our picture back in. And they kind of gave us a hint about that by the way they've constructed their diagrams. So you can see they've drawn in the outer rectangles for us. The area of those would clearly be bigger than the area under the curve. That's basically what we're doing here. So I mentioned something about, well, because it's increasing, I know those outer rectangles will always be. Because, all right, there are missing ones in between there. And the only way the outer rectangle wouldn't be the way we're drawing them is, I suppose, if it started decreasing, then they might go underneath the curve rather than... But anyway, area of the outer rectangles is going to be greater than or equal to area under the curve. Thus, well, there it is. Mind you, we've got to work out the integral to prove it's 2/3 n root n. So we integrate, sub in, and sure enough we get 2/3 n root n. Okay, it's not looking too bad so far. The next bit, now we're going to get that same pattern, but this time we're going to prove it's less than or equal to 4n plus 3 on 6 root n using induction. Okay, well, test for n equals 1. Left hand side, square root of 1 is 1. Right hand side we get 7 on 6. So yes, it is less than or equal to. In this case, it's less than. Some people get caught up about this because of the equal to. Go, but it's not equal. It doesn't have to be equal to. Remember what you're saying. Less than or equal to. And it has to be one of those two things. Okay. So our result is true for n equals 1. We will assume it true for k. There's my assumption. We want to prove it true for k plus 1. That is what I'm attempting to prove. So it's a series type, so again we'll write it out, sum to k plus 1. Sum to k was my assumption. We said that was less than or equal to 4k plus 3 on 6 times root k. What was it on the other page there? Was it 4? We wanted 4k plus 7 on 6 roots k plus 1? Okay, so somehow we've got to create that. Well, I've made it all one fractions because we know the final result's going to be a single fraction. It's going to be on 6, so it kind of makes sense. Let's make it as one fraction, all on 6. You'll also notice the 4k plus 3 I've put into the surd. So I multiplied it by root k but made it an entire surd. Remember, we're trying to show it's a multiple of the square root of k plus 1. So ideally, this first square root, I'd like to have a factor of the square root of k plus 1 as well that I could pull out. So I'm working out, we've got 16k cubed, 24k squared plus 9k. Now k plus 1's not a factor of that. We would get a remainder. If I did a polynomial division there, divided by k plus 1, I get k plus 1, 16k squared, plus 8k, plus 1, but I got a remainder of minus 1. But of course, we're playing with inequalities here, not equalities. As long as I can preserve the inequality, I'm okay. I am subtracting 1 from whatever's under the square root sign. So I've got to get something smaller. Sorry, before I've made it smaller, I factorised for the 16k squared plus 18k plus 1. But that must be smaller than if I didn't have the minus 1 there. It's 1 bigger under the square root sign. Now that has the factor of k plus 1 that I'm looking for. And the square root of 4k plus 1 squared is 4k plus 1, and 4k plus 1 plus 6 is 4k plus 7. That's what I'm looking for. Hence it's true for k plus 1, if it's also true for k. Oh, it's been a long time since I've concluded like that. That's how we used to do it. We don't do it anymore, remember. We don't conclude it. We just go, hence by principle of mathematics. But that's... Okay. So the next part, we're going to use those two previous parts to now work out, or estimate anyway, what the square root of 1 up to the square root of 10,000 is. We've basically trapped the square root of 1 up to the square root of n between two expressions. So we want n to be 10,000. Let's see what happens. Well, the left-hand side to the nearest 100 is 666,700. And the right-hand side to the nearest 100 is also 666,700. So if I've trapped it between 666,700 and 666,700, it's a pretty fair bet that our estimate is going to be 666,700. Because I guess the thing to make note of with this question is, if you couldn't do B and C, you could still do D, because at least they've told you the two expressions that it's trapped between. So you can still go and at least use that and get some marks there. Oh, a classic one. Prove x is greater than the sine of x. All right, I'll do it graphically. There's y equals x. Ooh, there's y equals sine x. I only want for x is greater than 0. No, I can't just say, oh look, the line's always above it. I know function x is x, there's my straight line. So the derivative of function x is always 1. So the slope of that line is 1. That's a really long way of just going about saying the slope of y equals x is 1. Why on earth didn't I just say? Anyway, the sine graph, the derivative is cos x But hang on a sec. In between 0 and pi on 2, not including 0, we know cos x is always less than 1. So at the point 0, yes, they would have the same slope. But after that, the slope of the red curve is shallower than the blue curve. Well, that means the blue one's increasing quicker. So it must be above it. Must always be above it. X increases faster than sine x. So therefore x must be bigger than sine x in that interval, that specific interval. Now, after pi on 2, well, sine now goes back down. X is carrying on going up and up and up. So look, I mean, after that point, it's, well, you hate saying it's obvious, but we know sine x is always going to be less than or equal to 1, and x is always going to be greater than, so x has to be greater than sine x for greater, combining the two, x is greater than sine x for x is greater than 0. Alrighty, so that's all we'll deal with inequalities today. So tomorrow we'll look at the more interesting sort of, or not, these aren't interesting, the more interesting problems.